Most of my effort these days is functional work. I'm actually working to help the Institute prepare for the James Webb Telescope and prepare the ground system, it's called, the software and the systems that will support the James Webb Telescope and astronomers to propose for the James Webb Telescope. And so most of my effort is in meetings and that kind of stuff now, but I do have a bunch of good collaborators, and over the last 6 or 7 years, we're partway through a research project that I'll eventually get to tonight. I want to tell you some other things first before we get there. On this galaxy M83, and in the background here you see what is a large mosaic image from the Hubble telescope, one of the data sets that we took for this project to help us look at the star formation, huge amounts of star formation going on in here, and then find the supernova remnants, which is the stellar life, the birth and evolution of stars, and then the stellar death is the back end, the supernovae, and the remnants, the things that they leave behind. And we try to study that galaxy and put it in context with our own Milky Way galaxy and other galaxies here in our local group, for instance. Okay, so before we get to the meat of things here with the star formation and the supernova remnants, I want to spend a couple minutes giving you some context and tell you about how we find the supernova remnants in other galaxies. We'll talk about what we see locally and what we're trying to find as we look farther away, and then we'll get into M83 itself and what we are finding and some ideas of what it might mean. So part of the context I like to do, I like to try to do a few things to make big numbers understandable. You know, we hear so much, in the public domain these days, we hear millions and billions and trillions thrown around, and they're just big numbers. We just don't understand how big numbers really are. And in astronomy, of course, we have to deal with a lot of big numbers. We have the problem of distances. I mean, 1 light year, our yardstick that we use in astronomy, is some 6 trillion miles, 6 times 10 to the 12th, a 6 with 12 zeros, miles in 1 light year. And the nearest star is 4.3 light years away, but the distances to quasars and galaxies are millions or billions of light years. And so these are just big numbers. They kind of lose their context. The same thing with discussion in the public domain when we talk about budgets and this kind of thing. And I think part of the problem is, we kind of hear million, billion, trillion, and we think they're kind of factors of 10 apart, but they're not. They're factors of 1,000 apart. It's 1,000 millions make a billion, and 1,000 billions to make a trillion. Okay, so I thought I would just do a little exercise to give you some idea of how big a billion is. Okay, and so I have some props here. I have a ream of paper. I want you to use your imagination here a little bit. Okay, so the ream of paper has how many sheets of paper in a ream? Do you know? 500. 500 sheets. Okay, let's assume every sheet of paper in here is a $100 bill. Okay, so we got 500 $100 bills. That's $50,000 right there. Okay, so if I take 2 of those, we got $100,000. So that's a little easier to go by factors of 10. So there's $100,000, $100 bills side by side, and I got a yardstick here. That happens to be about 4 inches. Okay, so 4 inches of paper is like $100,000. So 10 times that is $1 million. Okay? If we had the stack of paper that high, that's a meter thick, 40 inches, that would be $1 million. So $100 bills stacked up to there is $1 million. $1 billion is 1,000 times that. A kilometer, 0.6 of a mile. Okay? So when you hear, just to pick a random number out of the news, 913 million, that's over half a mile high stack of $100 bills, folks. So that's a big number, okay? Big numbers. So let's do one more thing. Let's go one more step. Instead of money, let's talk about time, because time is another thing in astronomy that gets pretty hairy for us, and it's because there's such a dichotomy between our experience of time, where 100 years is a long time to us, but to realize that 1 million years, or in some contexts, even 1 billion years in astronomy is considered a short time, because the universe itself is 13.8 billion years. And so you're looking at the evolution of galaxies from early times on. You know, a billion years is really not that long, believe it or not, right? So we could do that same thing. Let's take one sheet of paper, and this is now a timeline, okay? One sheet of paper is 100 years, a human lifetime, a long human lifetime, okay? Well then, a million years is that big, and a billion years is the 6/10 of a mile, 1 kilometer tall. So this is a short time in astronomy. One sheet of paper is a long time to us. And that's why we sometimes have a hard time communicating these big numbers. Well, so now we're going to look at star formation in M83. You collapse a cloud of gas and dust, it creates a whole bunch of stars. There are a whole range of different masses. The big massive stars only live for a few million years. Short time, okay? Whereas, I mean, our sun we know is 4.5 billion years, is only maybe about halfway through its lifetime. So the low mass stars that form will stay around almost forever from an evolutionary standpoint, for the galaxy standpoint, whereas it's the most massive stars, the ones that live fast and die young, that create most of the energizing of the interstellar gas, forcing new star formation to happen as those shock waves from the supernovae impact clouds of gas and dust and make them collapse and so forth. So I'll probably mostly concentrate on the more massive stars and the supernova remnants that come from those massive stars as we go on through the talk. The other piece of context I wanted to give you is we all love these beautiful color pictures that we get out of Hubble and out of other missions as well. And I wanted to put that in context a little bit as well. This is the Kepler supernova remnant. It came from an explosion that Johannes Kepler observed in 1604. One of my favorite objects here. And what we're looking at in this color picture is actually a combination of Chandra X-ray data, two different colors here, blue and the green in this picture. This is harder X-rays that show you kind of the outer rim is the brightest. That's the shock wave in the hardest X-rays. The green is a little bit interior to that. That is the actual ejecta, the star stuff from the supernova that exploded. Okay. The yellow, which I show in more detail on the other side here, but you see the yellow in here is the densest clumps of stuff. That's what Hubble sees, is the really dense stuff in the optical. So the yellow is Hubble, and this is one wavelength of infrared emission from the Spitzer Space Telescope. It's actually showing us warm dust that is heated by the shock wave. And you see how it's one-sided, how one side of the structure is really dominant in the heated dust. And it turns out, putting all this together, that this is telling us that the shock wave is running up a density gradient. It's denser up there in the upper right, and the dust is denser, and it's getting heated up by the shock wave as it impinges on that denser material. So again, looking at things at different wavelengths, one of the points here is that supernova remnants observe across the light spectrum, from X-ray all the way out to radio. I don't have radio on here, but they're strong radio sources as well, infrared, optical, ultraviolet, across the spectrum. They're very multi-wavelength, and so that's why I'm taking a multi-wavelength approach to look at this galaxy, M83. We have to look at different wavelengths to find the ones that are bright in X-ray versus the ones that are bright optically, and so forth. Okay, so when we make these color pictures, everybody kind of knows this, but I just wanted to point out that, you know, if I make one image in red, one image in green, and one image in blue, then where things are bright in more than one band, you get different colors. Okay, if it's bright in the blue and the red, you get this kind of pinky magenta color. If it's bright in blue and green, you get that cyan color. And if it's bright in red and green, you get yellow. And so if I make a color image out of 3 different images of different wavelengths of light, or different data from different instruments like we just looked at from Chandra and from Hubble and so forth, you can compare the similarities and differences by looking at the colors where they're both bright. That's one of the tricks we play. And then over here, I just show that basically it's not an on-off thing like this. Basically there's all kinds of gradation in the color that you get as you combine those in different amounts. So as we make color pictures, we can actually use that to diagnose what's going on if we understand what the images are that went into the pictures. Okay, so one of the problems that we have just looking locally, you say, why do we look at M83? Look, 15 million light years away in another galaxy to find supernova remnants. We've got ones in our own galaxy that we can look at in great detail, and indeed we do. But part of the problem is that we have very few of these very young objects that we can look at and understand and kind of put together the big picture of what's going on. This is the Crab Nebula with Hubble, 3 different wavelengths of Hubble light put together into a color picture here. And this is the Cassiopeia A supernova remnant, which is a much more massive star that blew up in our galaxy. This is the same color coding that I had on that Kepler picture a minute ago, where the yellow is the Hubble and the red is the infrared band, and the blue and the green are the X-ray. And you can see how they all mess up there in this explosion, which is expanding at very high velocities, even some 300, 400 years after the explosion, still expanding at 10 or 12,000 kilometers per second. Interestingly enough, the Crab Nebula, almost 1,000 years old, and it's only expanding at 1,800 kilometers per second, and we think it came from a much lower mass star. So let's say we have half a dozen of these kinds of objects or something like that to look at. We've got the mass varying, we've got the expansion, the age is different, the expansion velocities are different. How do we take all these pieces of information and put it together into a picture when we have so few objects to kind of put together and make that picture? And just as another sign of how crazy these are, this 8 or 10 solar mass star, we know, produced this crazy Crab Nebula pulsar down here in the center of the object that is actually what's energizing and actually accelerating the expansion of the material from the explosion. Whereas this big monster 25 solar mass star that blew up here made this wimpy little neutron star down here that we don't even see any pulses from. So there is a stellar remnant left behind from the explosion, but it's not anything that would knock your socks off like the Crab Nebula pulsar. So very few objects to understand the parameter space, and many things changing. It makes it hard. And so we'd like to find a lot of these young remnants and look at them, especially if they were all at the same distance. You take the distance difference out of it, you can look at that sample of objects that are all at the same distance and understand systematically what's going on with massive star supernova remnants. So that was one of the motivations for going to M83. All right, so I'm going to leave the Crab Nebula behind now. That's kind of at the lower end of a massive star. These are 3 supernova remnants of we think, very massive stars. Here's Cass A again in our galaxy, and below here I just have a blow up of some Hubble data that shows some of the detail in this stuff. This is star stuff. This is the guts of the massive star that blew up, and the material is still in the process of flying out into space at very high velocities. And eventually it will blend back into the interstellar medium and maybe participate in the next round of star formation that will have higher abundances than the current ones do. Okay? This is an object in the Small Magellanic Cloud that is very similar to this, only it's larger, it's older, but the only thing we see with Hubble, this blue stuff that you see in that picture, is almost pure oxygen. It's from the layer of the star that produced oxygen. If you took a spectrum of that, you would see there would be some neon and some other things in there, but you see no hydrogen. It's all the star stuff that's flying out into space. This object is in the Large Magellanic Cloud, a neighboring galaxy of ours, and it is larger. It has a kind of an outer shell here that's starting to form from the blast wave going out into space and starting to sweep up surrounding material. So you're getting that outer shell starting to form. But down in the center here, this blue and green stuff in this picture is this kind of stuff. It's the star stuff, still visible, even though it's a much, much older object. And to put those 3 in a little more of a context for you, in this graph, I try to show you their relative sizes to give you a little sense. So Cass A, 340 years since the explosion, 18 light years in size. EO 102, this one with the phone book name, is about 1,200 years old and is a little over 40 kilometers per second. This is expanding at, say, 10,000. This is 2,000. And over here, the outer structure is not expanding rapidly, but that green stuff, the oxygen stuff in there, is still expanding at 1,000 kilometers per second, even some 3,000 years or more after the explosion. And so if we wanted to find this kind of object in other galaxies, we would want to look for high velocities and we would want to look for these funny abundances compared to the surrounding gas. And that's one of the ways we try to find them. And just taking that one step further, I like to make this point because this is thought of as a young object. The Veil Nebula, the Cygnus Loop, is thought of as kind of an older or middle-aged object, and yet this is the relative sizes again, not too different. 88 light years versus 82 light years in size. Again, this outer shell is thought to be sort of the wall of a cavity that was blown by the wind from the star before it blew up. So there's a cavity that it's expanding into. That's the same model we have for the Cygnus Loop. This bright emission on the outside edges where the shock wave is finally starting to hit the outside edges of a cavity. So the two stars that blew up here could be very similar to each other, and yet we don't see the oxygen-rich, the ejecta in this one. They're starting to tease it out of very deep X-ray observations of the Cygnus Loop. They're starting to see some of that enhancement. But most of that stuff is blended back in or faded away at this point. And so this object is on its way to becoming something like the Cygnus Loop, and they're about the same size. This has nothing to do with the rest of the talk, but I had to throw it in here. You see this little white box on the side. There was this wonderful picture of the Cygnus Loop, just that tiny little section that was released last year. That makes the point also that you use the different colors to represent things. So we've got an oxygen, a hydrogen, and a sulfur band in blue, red, and green. And then you can see how the colors are mixing together. You get the yellows, which means that the H alpha and the sulfur 2 are bright. You see places where the blue is dominant, where the oxygen, high ionization oxygen is dominant, and so forth. So you get some sense for how you get diagnostic power out of the color images if you understand something about what's going into the picture. But that's just a spectacular picture. This cloud up here is probably unrelated directly to this. It's either the foreground or background. It just happens to be in the frame here. And there's a one light year bar across there. So the whole object, of course, is much larger. We're looking at a tiny little piece of it. And this Hubble picture, is 18 orbits of Hubble data, about 100 separate images in those different filters, all aligned and put together. This was actually 3 by 2 with C3 fields of view for the Hubble telescope. So this has been all stitched together for six fields of the wide field camera to put together this picture of that one little piece of the Cygnus Loop. Hubble's job is to look at small areas of the sky in very great detail. That's its reason for existence, basically. Okay, well, we're almost M83. I just want to kind of give you the big picture here first. I mean, the idea, remember, is that we want to understand the star formation processes and the whole evolution of stars, and we want to do that for galaxies in the local universe. It turns out M83 is a prime testing ground for doing this, because you want to understand, by comparing local galaxies to more distant galaxies, whether these processes that guide this stuff are universal processes or whether there are differences. And the part that I'm really most interested in and most involved in is in finding the supernova remnants, which is just the one part of this bigger picture. So most of the rest of this I'm going to be talking about trying to find the supernova remnants and telling you how we do that. So here's a ground-based picture, very nice ground-based picture of M83, about 15 million light years away. 1 arc second is about 72 light years. And 1 arc second is kind of, as you're a lot of amateur astronomers out here, I presume, or people that know that's basically kind of what you get from ground-based observations is about 1 arc second, or sometimes a little bit worse, sometimes a little bit better. But of course, Hubble can do about 20 times better than that. So we're getting down to just a few light years type resolution with Hubble pictures when we look at this thing that's 15 million light years away. And we can still resolve things at just a few light years in size. That's pretty spectacular. Okay, it's called a barred spiral galaxy. There's certainly other galaxies that have more prominent bars, but you can see it's kind of extended here. It's got this very bright nucleus where star formation is just happening in a tremendous burst. But you see also a lot of these H2 regions around out through the spiral arms where star formation is happening. It turns out this galaxy is a great place to look for supernova remnants because it's produced a ton of supernovae. We've actually seen over the last 100 years 6 supernovae in M83. We found another object that I'll mention briefly as we go along that has to be less than 100 years old that was probably a supernova that we did not see Maybe it happened when M83 was behind the sun. We don't know exactly. But anyway, there's another one that's young. So probably 7 of them in the last century. Interestingly enough, none since 1983. We are due. We are due. We had 7 of them in the first part of the 20th century, and now none since 1983. So we ought to be seeing some supernovae coming from M83 pretty soon. And just for context, again, this is a 1/4 of a degree field of view that I'm showing here. Of course, the full moon is about a 1/2 a degree across, so it's a sizable galaxy on the sky. But interestingly enough, if you put this where the Milky Way is, this whole thing is, you like put 2 side by side and 2 up and down. That would be about the size of the Milky Way galaxy. So it's actually a relatively small spiral galaxy compared to our Milky Way. I mentioned that it had 6 or possibly 7 supernovae. Here's where they are located across the galaxy. Some of them are very close to star-forming regions. Some of them are not. One is right down here in this bright nucleus where there's tremendous activity going on. Near star formation, again, near star formation up here. I'll talk about this object and this object. This is the one that I think we found that has to be young, but the supernova was not seen. But the point is, with this many supernovae, less than 100 years old, if we want to take, what do you want to take, 1,000 or 1,500 years as a young supernova remnant, there ought to be 60, 70, maybe even 100 of these young ejecta-dominated supernova remnants in this galaxy. And so that's why one of the reasons we wanted to look here. We also wanted to find the normal supernova remnants like the Cygnus loop, and so the search actually looked for both of those things. So just very briefly, we used a large ground-based telescope here at Las Campanas Observatory for a ground-based search, and we actually found 225 supernova remnant candidates from that ground-based search. So the question is, why do we need Hubble? Well, we could find them, but we couldn't measure their sizes from the ground. Even with very excellent ground-based data, most of the objects we wanted to get, see if they had shells or if they were very small objects or whatever, we couldn't do with Magellan, and so we had to do that with Hubble. And so down here is the Hubble part of the project. We also have 730 kiloseconds. That's a lot of time on the Chandra X-ray Observatory to take a very deep X-ray picture of this galaxy. We found 440 point sources and lots of diffuse emission. I'll show you that. And then there are other data sets that we're working on, including radio, again, multi-wavelength, spectroscopic follow-up, and I'll show you a couple of spectra from that as we go along, but I basically won't talk about those very much, that part of it. So there is, I showed you here the optical picture of the galaxy, right? And here is this deep X-ray picture of the galaxy to approximately the same scale. You can even kind of see the spiral arms and that red diffuse gas there. You see this incredible X-ray bright region associated with the starburst nucleus in there, and all these little point sources. And the vast majority of those point sources are actually in M83. A lot of the brighter whitish looking ones are X-ray binary stars. And you can see that because some of those sources vary over time and whatnot because they're in binary orbits. And the things that don't look too impressive on here, a lot of these little red dots or yellow dots in places oftentimes are associated with optical supernova remnants. So we have a lot of supernovae that show up. The color coding here goes from relatively low energy X-rays in the red up to the higher energy X-rays in the blue. And so this diffuse gas, this is the brightest diffuse X-ray emission that we have seen in any spiral galaxy, by the way. So if it doesn't look too impressive to you, you should see some of the other galaxies. This looks pretty good. Just that tells us that there is hot, low-density gas permeating the spiral arms of this galaxy, and that has been energized by the stellar formation, the winds from the stars, and the supernova explosions over time have energized the interstellar medium of this galaxy, and we get this incredible bright diffuse emission. Also, just a little blow up and rescaled so that it's not burned out. This nuclear region has a tremendous number of point sources and diffuse emission in there as well. It's a very complicated region. Some of those, again, are aligned with supernova remnants, and other ones are X-ray binaries in that very active nucleus. But it's so confused in there, we've mostly set that aside and worked on the outer part of the galaxy. The big picture here is that M83, although it's hanging out there, it looks like a nice big bright spiral galaxy all by itself, is actually much more extended than we give it credit for. This is the part we've been looking at here, the bright part. This is Galax ultraviolet images, and the red in this picture is actually radio H1 emission, hydrogen emission, that shows that there is very faint diffuse gas way out there, and the blue light that you see way out here is star formation that is actually happening way out here away from the bright part of the galaxy. This probably indicates that at some point in the not too distant past, M83 had an interaction with another galaxy, and we don't see that other galaxy right now, but it was enough to really disturb the outer structure of M83, and maybe what triggered this big burst of star formation in the galaxy itself. So that's a much larger scale picture than what we were looking at before. Okay, so how do we find supernova remnants? These are spectra. Aren't they beautiful? People like rainbows for spectra. For an astronomer, a graph of intensity versus wavelength or versus color, blue to red. In this case, these are optical spectra. Intensity, these are spectra to an astronomer. And what you see here, you see some low-level noise going across here, but then you see these spikes that go up. This is called an emission line spectrum. If you look at a gas cloud, an H2 region, or a supernova remnant, you see emission lines, these spikes in the spectrum. Okay, and the relative intensities of the spikes change as you look at different objects, as you look at different kinds of objects. Okay, so this is a shock-heated supernova remnant, and what you see is that this little line of sulfur out here is much stronger relative to the hydrogen, and there's actually nitrogen lines here right next to it. The sulfur 2 jumps up. These sulfur lines jump way up. The oxygen lines in M83 get very strong in many supernova remnants, not all of them, whereas in the starlight ionized gas, the oxygen is very weak, the sulfur is very weak. So knowing what the spectra look like, now I want to say, let's go and take pictures, and we're going to take little filters that just get the light from pieces of the spectrum, and we're going to take pictures, and then we're going to do an RGB of these filters and look for color combinations that will tell us which objects have strong sulfur 2. Okay, and that's how we find the supernova remnants. For the ejecta dominated guys, it's a little bit different. This is a spectrum, an integrated spectrum of Cas A in our galaxy. First thing you notice, of course, is the lines are huge, broad lines. That's from that high velocity of the ejecta still moving. They aren't all that broad, but they don't have to be that broad for us to see it. They just have to be broader than we see in these kind of spectra. So if you saw these things broadened, you would know that you had high velocity. Cas A, okay, so here's my oxygen filter. Here's my H-alpha filter. There's almost no H-alpha, and what's there is not really related to the Cas A. And then there's a sulfur 2 filter here. So this object would look bright in oxygen, bright in sulfur, and almost no H-alpha. Or some of the oxygen-rich remnants don't have sulfur either, so that would be bright here and not much in either of those two bands. And so if I found things, if I color-coded this blue, let's say, then things that look really blue ought to be dominated by the O3 emission. So that's how we find the ejecta-dominated guys, or we try to. We can get confused with just the optical data here because planetary nebulae from low-mass stars also can have strong oxygen 3. And so the other thing we need is, like Cas A, we know we have this really strong soft X-ray emission as well. So we need to see something that's bright in oxygen and has an associated X-ray source, and then we're pretty sure that we've got an ejecta-dominated remnant. Otherwise, it may just be a planetary nebula. So here's the trick. All right, we put H-alpha in red, we put oxygen 3 in blue, and we put the sulfur 2 in green. Now, the sulfur 2 line is actually in the red part of the spectrum, but if I did red, red, and blue, I don't have any diagnostic power, right? So I made the sulfur 2 green, and now things that are yellow are strong in sulfur 2 and H-alpha. Those are the normal remnants. If I find things that are blue or in the cyan, I'm pretty sure that I've got something that might be the ejecta-dominated thing, and that's the trick that we play. And so here's a little example, and I'm showing you the black and white images individually first, and then here's the color image down here that I'll get to in a second. So the trick also is that when we take images in these emission line filters, you also get some starlight. And so you take a picture that just gets the stars, and you scale that and subtract it away. so that you get a pure emission line image. So here, except for maybe a few little stellar residuals like this, this is the oxygen 3 emission only. Here's the H alpha emission only, and here's the sulfur 2. And you can do ratios in black and white, and you can find things, right? Like here's the ratio of sulfur 2 to H alpha, and there's kind of three regions that pop out here. And it turns out, here they are in sulfur 2. There they are in H alpha. This was pretty confused, but these two, you can see they're about the same brightness in sulfur 2 and H alpha, and sure enough, they pop out in the ratio. What's really neat here is that even though there's all this photoionized gas around the region, you can still pull out in the ratio that there's actually something with enhanced ratio buried in that H2 region. So there's 3 supernova remnants right there. You could look at the O3, and here's these two actually happen to be fairly strong in oxygen 3 as well compared to H alpha. And so let's look at the color picture. The ones that are bright in all 3 are kind of whitish or even a little bluish because they've got so much of that oxygen emission. But we already looked at the ratio of the sulfur 2 to H alpha. We know those are high. This guy does not have very much O3, and so it comes out looking kind of greenish yellow, combination of the H alpha and the sulfur 2. So that all kind of hangs together. So you say, wow, look at that guy. There's a nice bright, possibly oxygen-dominated supernova remnant, right? Well, it turns out that's a planetary nebula in M83. There's no X-ray emission associated with that, and so that was a close but no cigar in that case. So with Hubble, what we do is we go and we get the size of these guys, and then we actually find some additional objects as well, because in those confused regions at ground-based resolution you can't find them, and sometimes to Hubble that they pop out. So here are 7 fields of Hubble data with C3. These 2 green ones were actually taken shortly after the last servicing mission when the camera was first installed, and then I came back with a team and we got these other 5 fields to kind of round out the coverage and get most of the galaxy. And we looked at it with a bunch of continuum filters, the star filters, and then we looked at it with a bunch of these emission line filters and played this game over that whole galaxy. And that's what it looks like when you stitch it all together. And thanks to Zolt LeVay here at the Institute for putting that pretty version of it together, but also thanks to a couple of folks here, Jennifer Mack and Derek Hammer, who were the ones that figured out all the alignments and all the tweaks to get it all lined up properly so that Zolt could work his magic on that picture. And if it looks sort of familiar to you, but not that familiar to you, well, if you kind of cut off this little wing out here and just made a nice rectangle out of that and turned it around sideways, you'd get this nice picture of the version that was put out as a press release back in January 2014. That's the same data set, scaled a little bit differently, shows the stars a little bit more dramatically, and so forth. But that's a pretty famous Hubble picture now, and it's the same data set that I'll be talking about. So it's nice to look at the beautiful picture of the whole galaxy like this, but the real power of Hubble is when you start zooming into it where you can see the details. And here are a couple of, this is still a very large area, 5,000 light years across, showing dust lanes, the star formation going on in here. This is a little closer in toward the nucleus. You can tell from the background, and you can just see the tremendous dust lanes and stuff in this galaxy. But behind that, these tremendous regions of star formation also going on. The red regions, of course, are where hydrogen gas is being ionized by the starlight. That only happens for the first maybe 5 million years after a burst of star formation, maybe 10 million years on the outside edge, and you lose that H alpha emission, and it leaves behind the stars, and it might look something like this. Very young star-forming regions, very compact and condensed. You can see that there's bright light in there, lots of stars that are not even resolved, forming, but they're ionizing the gas around them. Then maybe a little longer along the way, that cluster of stars has had enough time, the stellar winds and a few supernovae have started to blow a bubble, and they're starting to move that stuff away from the site of star formation. And then maybe 50, 70 million years later, that material has all been dispersed, and you're left with a cluster of still fairly young stars, but you see there's a lot more red dots in here. Those are red giant stars, some of the more massive stars that have now started to evolve away from being blue and become red giant stars. So you can actually look at the stellar component and understand a lot about what's happening with star formation. Interestingly enough, we don't find supernovae in places like this. Now, it's partly because supernova remnants. I'm sorry, we don't find them in regions like this because the gas has all been cleared out. If you blow something up in there, it just expands out and it doesn't hit anything, so it never gets bright. So we no doubt are missing some supernova remnants that happen in that scenario, but we tend to find supernova remnants in regions around regions like this. And so, for instance, here is one example, and I'll just real briefly tell you, I'm not going to talk about this in any detail, but there's an infrared iron 2 line that Hubble's infrared channel can observe that turns out to be a very nice diagnostic for shock-heated gas. In this case, we're losing the data up there, but you can see that this H2 region that's associated up here just is not there at all in iron 2, and this little dot here is. That's a clue. White means it's strong in all 3 of my bands, right? It's not an oxygen-dominated guy, but it's bright in all 3 bands, whereas that photoionized stuff is not, and so that's a clue. And it's very tiny. This I don't have it marked on here, but that circle is 3 arc seconds across, so that's way below 1 arc second in size, that little dot. There's no star there, so it's not a subtraction problem or anything like that, and it's a strong soft X-ray source. So that is a young supernova remnant in M83. Doesn't look like much, but some of them are a little more extended. Here's a little region of M83 where there's 5 of them in one small region. And so some of these guys, this is the emission line band over here. You can see little shell shapes to these guys and whatnot, so they're resolved. This one's a little more funky up here. All of them are bright in iron, which is nice to see. As a matter of fact, here's one that's bright in iron that we don't see optically. We don't see an X-ray, and it's because it's against this dark lane. It's probably behind the dust, and this infrared line actually gets through the dust. And so we're finding ones that we would miss otherwise because we've got that iron picture as part of the thing. So there's 5 supernova remnants, one that was not known before, and here we can now come in and measure the sizes of those guys and actually use that to understand the evolution. So I like to show this one because this is basically a Cygnus loop, a big, 70, 80 light year across object. You can see the shell is resolved there. It's strong in iron 2. There's some stars in the region, but nothing that would contaminate it that badly, and it's a strong soft X-ray source. I have a spectrum of this one. Here's the oxygen lines and the hydrogen line that's in the blue part of the spectrum, and then this is the red part of the spectrum. You can see the strong sulfur lines compared to hydrogen and nitrogen, just what you like to see. And again, no evidence of broadening above the instrumental profile in the spectrum. So that's a Cygnus loop in M83, 15 million light years away. So we'll come back to the young remnants in a minute, but I wanted to talk about the historical supernovae again for a minute, and in particular, this object, 1957D, so that's a supernova that was observed in 1957, so we know how old that one is. And then this object down here that we found that I think is comparable in some ways to, well, it's definitely a young supernova remnant, and in some ways it's similar, in some ways it's different from 57D. So here's a couple of pictures. This is the Chandra X-ray picture. In this case, it's a blue, hard X-ray source, which is not typical for supernova remnants. They're usually these red colors. That might mean it's got a pulsar in it, because pulsars have a different kind of X-ray spectrum. Okay. At ground-based resolution, this is what it looked like. There was a blue dot, oxygen, blue dot, and it had some red stuff next to it, but we really couldn't see what was going on. And so these two now are the Hubble pictures that have been zoomed in to that little yellow circle up there, so we're just looking at that region. And sure enough, what do we see? Blue, dominated by oxygen 3, that's the 57D, and here's some H-alpha emission that's associated nearby, but it is not part of that structure that we see there. And so that should show broad oxygen lines if we know what we're doing. And sure enough, in the spectra, here we have the oxygen line, and it's very, very broad. Interestingly enough, from 1989 to 2011, when we got the last spectrum, it's actually faded quite a bit, but it's still there, still broad lines. It's associated with a little cluster of stars. This is Hubble data as well of the stars. And we can actually go in and do photometry for those stars and understand what the most massive stars that are in that cluster are. And the most massive stars are about 17 times the mass of the sun. So if this one blew up, it had to be more massive than that, because the more massive they are, the faster they go through their life cycle and blow up. So it tells us, it confirms basically that this had to be a massive star that blew up. So that's the 57D guy. This other one, just take a minute to explain. These are ground-based pictures. This is the Hubble pictures zoomed in again, so the scale changes between those two. And here's the spectrum of that object that we found after the fact. The story goes like this. We found this object in our ground-based data. We actually thought that it was a larger object and that this was a bright knot maybe on one side of the shell there. But when we looked at the X-ray data really seemed to line up with that bright dot up there. And so we came in with a spectrograph and took a spectrum of that dot, and this is what it looked like. And it's very broad lines, very high expansion velocity, so it's a young object. And the reason we found this with our three little filters, right? I put an H-alpha narrow filter there and a sulfur 2 filter there, and it looked like it was strong, and sulfur 2 to H-alpha, and yet it's got this huge feature that goes over that entire region of the spectrum. So I just got lucky on that one, and it does have the oxygen as well. So we found it as an interesting object, but we didn't know that it was had this high velocity until we got the spectrum of it. Well, now we bring Hubble into the picture because Hubble can see the bright knot, and it actually can't detect the low surface brightness stuff adjacent to it there. But here's H-alpha, sulfur 2, O3, just like filters got it, and but it's very, very tiny. It's just a dot. It looks like a star. It's unresolved. It's very tiny. So from the upper limit on the size of the object and the expansion velocity that we got from the spectrum, we can say that it has to be less than 100 years old. So this is the one that we think is a young supernova remnant where the supernova was not observed. Well, okay, so we're trying to find these young guys, and what did we find? Well, if we just look at the sizes of them, the ones that are less than 35 light years, 11 parsecs, forgot to change that, sorry, size, we found about the right number of objects. We've got 60 objects that are about the right size, that are tiny little supernova remnants. A number of them are X-ray sources as well. But only those two objects that I showed you, and one more that I'll show you in a minute, that looked anything like we expected for those ejecta-dominated objects. What do the rest of them look like? Well, they look like this, kind of like that one I showed you a minute ago. Here's another one. A tiny little dot, white, right in all three bands, not dominated by blue, by the oxygen. Strong iron source, strong soft X-ray source. There's a few stars in the neighborhood, fairly blue stars, so one of them blew up. And we take the spectrum. No high velocities. This object is the size of Cassiopeia A, and yet it has no high velocity material. And its spectrum looks like the Cygnus loop, or the other ejecta, or the other ISM-dominated spectra, the normal supernova remnants. It does not show evidence of being ejecta-dominated. So where are all the Cas A's? This is the third object that has some hope of being a Cas A. We don't have a spectrum of this one yet, but again, in oxygen, and there's no star right there. It's right on the edge of the bright nucleus of the galaxy. That right over here is the bright nucleus of the galaxy, so this is right on the edge. This guy, magenta colored, means it's bright in H-alpha and O3. It's not what we expect exactly, but it does have the strong O3, and it's very compact, and there's no star there. So I think if we get a spectrum of this, that we have some hope of maybe seeing high velocities in that one. So that's the third one that's kind of like Cas A. But we're not finding 60 or 100 of these things like we expected. And we found the young ones, and they don't look like this. So here's what's going on, apparently. We're not seeing counterparts to these local ones that we've seen where they get this big and still show evidence of high velocity and ejecta-dominated. We're seeing things the size of Cas A or the crab that already look like the Cygnus loop, that have evolved beyond the ejecta-dominated phase into this phase where you're looking at shocked interstellar gas surrounding the object. So the supernova remnants in M83 are evolving very quickly beyond the ejecta phase and into what's called the radiative phase of evolution. So we didn't find what we expected to find, and these cards will be on sale in the lobby if you want to buy one and send it to me after the meeting, because sometimes it doesn't work out the way you expect it to work out, But so I guess this is probably the most appropriate one for my situation. If you. But when science gives you lemons, well, you make lemonade, right? And so we've learned a lot. We've learned some really interesting things about this galaxy. And a couple of things that I really didn't highlight to you too much. I'll do number 2 here first. Basically, M83 has very high chemical element abundances, even compared to the Milky Way. We had the Small Magellanic Cloud, the Large Magellanic Cloud, the Milky Way, and M83. The abundances go from about 0.2 times the Sun's abundance to about 0.5 in the LMC to the Milky Way abundances. This galaxy has twice solar abundances over that entire galaxy, and probably even higher in the center. And I think those high abundances are part of the story. The other part of it is this X-ray data, remember, shows all this diffuse hot gas in the spiral arms. That's high density, high pressure gas in the interstellar medium of M83. So let's put these two things together. High chemical element abundances in a massive star allows the star to have a very strong wind that would blow material off before the star explodes. But if we've got a hot, high pressure ISM around it, that stuff can't go very far. It hangs out right around the outside of where the star is going to explode. So when the star explodes, it rams into that stuff very quickly, and you get a bright radiative supernova remnant very quickly at a small diameter. And so I think that's what's tricked us here. We're finding the young remnants, but we're not catching them in that ejecta-dominated phase that we were hoping to find. And it turns out this is very interesting, and we're still trying to piece together models and things that would help us understand exactly how that all transpires. But that's our working model for what's going on. So, in summary, basically, we did find a lot of young supernova remnants, as we expected, but we did not find them to be in this ejecta-dominated state that we did expect. And I just talked about the reasons. I hope as we get additional spectra for some of these candidate objects that we might find a couple more of those young objects with the very broad lines like that one that I showed you. But that's no guarantee, and it's certainly not going to get us up to 100 of those young objects that way. So that's it.